Thank you for joining me today. I will be sharing some examples of how cities have leveraged dispersed small-scale interventions to manage stormwater within a watershed. As cities have grown and agriculture intensified, the volume of runoff has accelerated into natural waterways. The EPA lists agriculture and urban runoff as leading sources of water pollution. The space for conservation measures to prevent and mitigate pollution is limited in both urban and agricultural contexts. In urban areas, space is limited as a result of density, while in agricultural landscapes, space is limited to maximize the square footage of crops. Space for pollution, prevention, and mitigation is limited in both urban and agricultural contexts. Our approach to managing water in rural and urban environments is often severed. However, the hydrologic system that they are a part of are connected. The new Bolton Center is a campus, a mini city, with its own infrastructure and water management system, combined with livestock and cropland nestled within two watersheds. The landscape is productive. It's a machine, but where may additional opportunities for water management exist? First, we must understand why cities have begun to improve their waterways. The Clean Water Act and the creation of the EPA mark a clear shift in a national approach to water management. The Clean Water Act and EPA have led to improvement of water quality by first targeting industry and then adapting their approach to include cities. Today, a leading contributor of point source pollution. In urban landscapes, the subgrade network often falls into two categories: combined sewer systems and separate sewer systems. Combined sewer systems are found in 772 cities in the United States and often result in combined sewer overflow, or CSO events, where stormwater and raw sewage combine and are released into nearby water bodies untreated. Newtown Creek, located in New York City, has 22 CSO outfalls that can be triggered by as little as 1/10 of an inch of rain. Recent modeling suggests that over 1.2 billion gallons are discharged annually. The focus on point source pollution from cities can further be demonstrated by the EPA's 1994 CSO control policy and the 2000 amendment to the Clean Water Act. These called for the development and implementation of long-term CSO management strategies. As a result, the EPA has issued 47 consent decrees to communities nationally with an estimated cost of over $32 billion to become compliant. This forced cities to be fined or reimagine their water management systems. New legislation required city and state agencies to coordinate with each other in new ways. This included the development of green infrastructure master plans, the formation of green infrastructure departments and task forces, and even new positions such as a chief resilience officer. This approach often included robust public outreach to help citizens understand the importance of these projects. New water regulations created the political will necessary to rapidly design, test, and deploy green infrastructure strategies in cities across the country. This approach often included a plan created by departments within a city to set clear and unified goals and action items. This led to the development of pilot projects to further test viable options to meet their goals. Pilot projects are constructed, monitored, and adapted until the city sets new design standards for large-scale implementation. The success of these pilots and standards are highly dependent on innovation from design professionals to develop designs that not only manage stormwater, but fit within the existing city fabric. The result has created new streetscapes, new and improved habitat, reduced energy costs, reduced the heat island effect, and measurably improved water quality. New green infrastructure pilot projects continue to broaden the potential of green infrastructure to continue to adapt to a myriad of complex conditions in the city. Green infrastructure has been proven to be a robust strategy for improving pollution from urban water systems. This has been an interdisciplinary effort. Teams of landscape architects, civil engineers, hydrologists, and urban planners have been at the forefront of designing green infrastructure to mitigate stormwater runoff. The New York City Department of Environmental Protection plans to construct 2,000 bioswales that can hold 4 million gallons of water per storm event, and more than 200 million gallons annually. Bioswales are roughly 20 feet long and 2 to 3 feet wide. As an individual element within a city, their impact is unimpressive. However, the deployment of bioswales as a targeted system-wide approach has radical outcomes. Like bioswales, there are many opportunities to hack conventional design standards to create innovative solutions. A network of small-scale solutions can have a large impact. A curb, an elevated highway, and a street end are all opportunities for innovation. These examples will illustrate how design can challenge traditional engineered solutions. Can we redesign a curb? And what benefit would it have? A curb is a simple but ubiquitous thing. San Francisco, for instance, has just shy of 5 million linear feet of curb. The operation of a curb, gutter, and apron is transparent. They facilitate the movement of stormwater from the road to a storm drain, or more recently, a bioswale. However, this straightforward gesture carries more than just water. Stormwater runoff transports pollutants, including sediment, nutrients from lawn fertilizers, bacteria, pesticides, metals, and petroleum byproducts, often discharging to waterways and often without treatment. Once in the waterways, removal of the pollutants, similar to that of microplastics, is challenging. Pollutants are ingested by fish, clogging their gills, impair water quality, reducing the ability for fish to hunt for food and reproduce. Pollutants bioaccumulate within the aquatic food chain and affect terrestrial animals and humans who consume fish and other aquatic animals. Pollutants are also found in drinking water. Although our drinking water is treated, according to the EPA, roughly 1/3 of public water systems in the US were a violation of the federal drinking water quality standards in 2016. Sediment also clogs bioswales and catch basins, sometimes resulting in localized flooding. A typical curb and gutter is designed for conveyance of stormwater only, and it does not provide any water quality benefit. Can we challenge the conventional design standards like the curb to do more? With widespread use of curbs, small-scale changes have the ability to have regional impacts. If we can design a better curb, one that collects pollutants before they enter the waterway, we can improve the health of our watersheds. A team of landscape architects and civil engineers at Ohio State University tested 21 alterations to a curb and apron. The data collected revealed that many of the designs met or exceeded the EPA's National Pollution Discharge Elimination System criteria to become a best management practice. These new designs can be used in concert with green infrastructure to reduce clogging or independently on roadways. Curbing sediment's small footprint can be advantageous in areas with mature trees and narrow sidewalks. Custom patterns could be developed for business improvement districts or by municipalities to adapt to specific aesthetic, hydrologic, and other physical conditions. Regular maintenance of curb, gutter, and apron designs can be performed by street cleaning machines already in use. Curbing sediment is a feasible alternative to the standard curb, gutter, and apron design. Widespread use of new curb designs can have large-scale impacts. For example, the city of Columbus has more than 14 million linear feet of curb. If applied across the city, this could capture thousands of pounds of sediment per year. Now a shift from stormwater on the ground funneled via curb into catch basin to runoff from elevated highways. The lower 48 states have 72 million lane miles of road. When these roads cross rivers, lakes, wetlands, and other impasses, the road often becomes elevated. Stormwater from elevated structures typically is held in a catch basin before it releases into a water body. Or, in some cases, a downspout directly releases water into the adjacent water body. Flushing Meadows Corona Park in Queens, New York is bisected by a series of elevated highways. The water from these downspouts flows into Flushing Bay, part of Long Island Sound. Modular pilot projects called Highway Outfall Landscape Detention, or HOLD systems, were developed to redirect water for treatment. Two designs were constructed. one from concrete and one from gabion. The concrete model, showed here, includes sedimentation basin to collect fine particulate matter and litter, gravel channels that carry water throughout the bed, and plants and engineered soil to treat stormwater runoff. This design can be used in an area where groundwater may be high or constructed above ground if utilities, tree roots, footings, and other conditions limit excavation. The gabion model has similar interior components. The pilot project was tested with a waterproof liner to collect output sensor data. However, the module is designed to be constructed without the liner, allowing for groundwater recharge once the water has been treated by the plants. The elongated sedimentation channel allows the planting to receive sunlight and avoid shade from the elevated highway. Curbing sediment and hold system respond to discrete conditions in the urban environment. What opportunities arise when you can redesign 40 feet of street? The Gowanus Canal in Brooklyn, New York was classified a Superfund site after years of pollution from industry. Today, much of the industry has left or changed course to comply with the Clean Water Act. However, canal water is still impaired by frequent combined sewer flow events. DEADEND Studio leveraged street ends along the canal, shown here in blue, to develop a modular network of street end sponge parks. The street end sponge park occupies a city easement for navigable waterways. The easement allows for 40 feet adjacent to a navigable waterway to be used for public use. The design provides access to the water's edge, small craft launch for the Gowanus Dredgers, a local canoe club, and manages stormwater from 2 city blocks. Without the sponge park, this water would flow into the canal untreated. The modular treatment cells allow for runoff to be treated by plants as it moves through the beds and engineered soil. The plants provide habitat for birds, insects, and is maintained by a local nonprofit. The pilot project was a collaborative effort between DEADEND Studio, their subconsultants, the Department of Environmental Protection, New York City Department of Parks and Recreation, the Department of Transportation, and many local stakeholders. With rapid advancement taking place in urban environments, landscape architects should consider how to leverage these successes and adapt them for rural, agricultural, and hybrid landscapes. The approach used by cities can be integrated into the new Bolton Center's campus. Within the campus, many standard conditions can be leveraged for further innovation. A riparian corridor, street, roof, parking lot, ditch, field, wetland, pasture, cropland, and lawn can all be asked to do more. The integration of new standards developed at the new Bolton Center can have regional impacts as visitors can see new productive landscapes. Not solely urban, rural, or agricultural, but a new hybrid landscape challenging conventional design practices of managing water.